Hi, I'm Chris Elrod, and I'm here to talk to you about Julia implementations of linear algebra routines, such as those traditionally implemented in BLAS and LAPACK libraries, such as OpenBLAS, MKL, and Apple Accelerate. What I'd like to do is outline a roadmap or vision towards how we may build a large Julia ecosystem of such functionality, and perhaps ultimately get to the point where we can make a Julia BLAS library available that is a fully featured BLAS and LAPACK suite, so that we can use LibBLAS trampoline and have all of our standard library linear algebra routines make use of these pure Julia implementations. The first question that we would be inclined to ask is why? Implementing a BLAS and LAPACK library is a significant undertaking. It would take a lot of effort that could be directed elsewhere. But more than just justifying our effort, answering why also naturally proposes the outline. That is because we're not beholden to the BLAS and LAPACK interface, especially not committing to it in its entirety before we're able to produce useful contributions to the Julia package ecosystem. On the note of interfaces, users rarely actually use the BLAS and LAPACK interfaces themselves. Rarely do you see somebody calling gem rather than mol. Rarely do you see somebody calling Potter rather than Cholesky. And then it's straightforward to, for example, use RecursiveFactorization.jl when one wants Julia LU implementation rather than LinearAlgebra.lu. So, with that in mind, our answers to why would naturally lead us to what we would implement first, and therefore guide us in our partial implementations before we ultimately get to a complete product. To answer the question why, we have three primary themes. The first being performance, that we can improve the performance of certain critical operations. The second being flexibility, that we can adapt routines to better fit specific applications. And the final being interop, that our Julia routines can interact better with Julia the language than CCall code can. So first, I'd like to discuss performance. Here is an example is single-threaded float64 matrix multiply, comparing an array of different libraries, LoopVectorization, Octavian, which is built on LoopVectorization, and then the three BLAS libraries, BLIS, MKL, and OpenBLAS. The x-axis here is size of each axis of a square matrix, and then the y-axis is the amount of G-flops achieved on a 10980XE CPU. Now, LoopVectorization's ability to get excellent performance on such kernels is already well known in the Julia community, but it bears emphasizing, again, because this is sort of taken as the gold standard of well-optimized routines, and is also a building block of many other functions. It's also not necessarily something that is easy to emulate for other libraries that are not relying on code gen, because they're traditionally, if you're not relying on code gen, dependent on handwritten assembly, and then for many different cases you would need to write different assembly code, which is something that is rather taxing or a Herculean effort, especially to then add support for new architectures or new vector extensions. A flashy but relatively straightforward example of an operation built up of many small single-threaded matrix multiplies is a larger multi-threaded matrix multiply. This particular CPU has 18 physical cores, therefore even for fairly large 500 by 500 matrices, each of these multi-threaded matrix multiplies is composed then of 18 fairly moderate size, fairly small sized matrix multiplies, and hence the ability to get excellent performance for these smaller sizes is crucial to good performance here. The second ingredient, of course, being that we have low enough overhead multi-threading such that multi-threading overhead does not dominate the runtime. To date, the biggest success story of Julia implementations of linear algebra routines is RecursiveFactorization.jl, which implements LU factorization and is used widely throughout the differential equations ecosystem for stiff ODEs. This benchmark here is using TriangularSolve.jl, a pure Julia implementation of LDiv, for the LDivs needed by recursive factorization, making that routine entirely Julia. The LU factorization itself is a recursive algorithm that recursively decomposes a matrix and uses repeated LDivs, matrix multiplies, and pivots, while the LDiv itself is built up of smaller LDivs and smaller matrix multiplies, so that even for a fairly large matrix that we wish to decompose in this manner, that decomposition is made up of many of these much smaller operations, and hence having excellent performance at those relatively small sizes gives us excellent performance even for relatively large sizes here. However, it is worth mentioning that multi-threaded implementations are not always straightforward, and here initial multi-threaded attempts at recursive factorization have led to very limited improvements in performance, moving from around 60 G-flops for the 500 by 400 matrices to 80 G-flops, despite having 18 cores available. Meanwhile, MKL managed to achieve a much more dramatic performance improvement. OpenBLAS, on the other hand, did fare actually more poorly than recursive factorization, having improved from around 40 to 50 G-flops at 500, and having actually lost performance for 200 by 200 matrices at smaller. But a lesson here is that simply multi-threading the building blocks is not enough, and that one has to probably put some more effort in designing an algorithm with multi-threading in mind to actually get good performance, considering perhaps the data movement between threads, for example, or picking blocks that can be computed in parallel independently at a more granular level as another means of limiting data movement. However, the takeaway here should be that even for 180 by 180 matrices or so, recursive factorization is still competitive with MKL, and then outperforms it by a rather substantial percent below that, which means that for stiff ODEs of size smaller than this, we are still able to get a hefty performance improvement through this Julia implementation, even for somebody using MKL. And it's also worth bearing in mind, especially now that AMD CPUs are so competitive in performance and increasing in market share, that MKL does not gain optimal performance on CPUs. So for much of the market and many new CPU buyers, they will really see probably great performance out of recursive factorization compared to any alternatives on such problems. And it also bears emphasizing that, when one does such an ODE solve, that it involves, many of LU factorizations, and that there's also a lot of workflows or a lot of, algorithms that may require a large number of such ODE solves. So it is easy to rack up huge numbers of these, such that one can have programs that take minutes or hours to run that are dominated by relatively small LU factorizations. For that reason, they are, or their performance really is a major concern, and not something that can be dismissed as, it takes just microseconds or milliseconds for one of these factorizations. Moving on to flexibility. Here I answer why it would be great to have infrastructure and tooling in place that makes it easy to implement such routines, just as is the case now for how LoopVectorization makes it easy to implement matrix multiply and similar rectangular operations that are fully associative, if one approximates floating point arithmetic as such. So this is in essence answering, or why it would be great to have to extend loop vectorization so that it supports multiple loops at the same level of a nest, and also supports handling of dependencies between iterations, able to track, for example, a store on one iteration being loaded again in another, and still produce correct results after aggressive transformations. It would be great to, or one example why it would be great to have something such as this is, if we came up with an algorithm that wanted to decompose a positive definite matrix not into an upper triangular matrix transposed times itself, but a lower triangular matrix transposed times itself, which would be equal to the inverse of the Cholesky factor of the inverse, rather than compute it that way through, which would essentially involve Cholesky factorizing the matrix using calculating or inverting the Cholesky factor and calculating then the inverse with that, and then factoring it again, and then inverting again. We could compute it directly simply by these loops, and then it would be great if we could go from such a loopy implementation into something that is actually optimal and able to achieve most of the CPU's theoretical flops, or at least most of them bounded by whatever the particular functions used here may allow. It's common practice in other languages to optimize code by trying to express it as sequences of BLAS operations. It's also not that uncommon within Julia itself. For example, tensor operations tries to convert Einstein notation into matrix multiplies, and similarly NNlib tries to, or does express, or does implement convolutions in terms of matrix multiplies. However, NNlib CPU, for example, much more naturally expresses convolutions as just a sequence of for loops, and is able to achieve 30 times better performance for these convolutions simply using turbo than depthwise M2 core does. Part of the reason it's able to do this is because it avoids the overhead of transforming data into the layout needed, and it is also able to, being a Julia function, and through Julia's JIT, is able to specialize on the particular sizes of the convolutions which the C libraries implementing BLAS are not capable of doing. Finally, Julia implementations of linear algebra and routines can interop better with the package ecosystem. And in particular, the tooling and infrastructure around it can be used in other parts of the ecosystem, such as by DSLs like Modeling Toolkit, as well as any potential array or linear algebra compilers used in the machine learning ecosystem. And LoopIRs could support AD transforms, for example, to give us high performance AD on loops. Additionally, while existing BLAS and LAPACK routines do support complex numbers, this would allow us to support a much greater array of Julia types that define basic operations like plus and times, such as dual numbers, colors, and multi-floats for high precision arithmetic. An existing example where we have already a high-performance implementation is TropicalGem.jl, which implements BLAS built on Octavian for tropical numbers, where times is plus and plus is max. These routines are useful for graph algorithms, for example. Another example of where we would interop better with Julia is with multi-threading, where currently it's common practice that when you have multi-threaded code or distributed code using multiple workers, that you set BLAS threads to 1, and then if you're going back to single-threaded code, then you might want to set BLAS threads to however many CPU cores or physical cores your hardware has available. However, by integrating threading with Julia, then whatever scheduler is managing it can potentially lead to much better workload balancing. I mean, a caveat there is that if these routines are going to be multi-threaded at all, that it's essential that we have low overhead threads, and that's why currently Octavian and LoopVectorization, for example, are built on polyester.jl to have minimal overhead on their threading routines. And as an example, what that allows is that if you have multi-threaded code using @batch, and this multi-threaded code calls a function making use of, for example, an @tturbo function, then the @tturbo will run single-threaded. But then if you call that function outside of your @batch, it will then run multi-threaded, essentially implementing breadth-first parallelism, and sort of automatically doing what some people have to, or what we often have to do manually via changing the number of BLAS threads. Putting this together, what does this mean for our roadmap? Well, essentially, it means that there isn't any rush towards implementing the full suite right away. Instead, I think every single piece that we implement should be something that we're adding because it incrementally adds something that part of the Julia ecosystem needs, such as the recursive factorization example needed by the stiff ODE solvers to get better performance than is currently possible with any existing library. And so that's sort of the direct approach. Additionally, the focus and most, I think, of the development effort towards this end should instead be on the tooling and infrastructure that will make it easier to implement any such libraries that part of the ecosystem may be able to make use of. In particular, extending loop vectorization to handle those more complicated loop nests, and then additionally adding, for example, cache level optimizations so that we don't need to then manually implement the blocking routines on top as Octavian currently does.